All right, so last section for this week is 4.3. And it basically looks at solving equations. Mostly, we might get to one or two inequalities that are rational problems. Okay, so most of the things we're going to solve algebraically. If we come across one that we can't, we can always use the graphing calculator to just sketch it for us. Again, we're not going to do the sketch by hand today. All right, and one of the problems we're going to look at involving rational equations is going to involve distance, rate, and time. Okay, so I just put the formula on the board just in case people didn't remember what the relationship was between those three things. Okay, so distance equals rate times time. Okay, any questions on that formula? It's pretty straightforward. How many people have already seen that before? Yeah, pretty okay. All right, so our first example, we're going to use this for a couple examples, but the setup is that Sue drove 30 miles to a train station and then completed the rest of her trip by train. In all, she traveled 120 miles. And it says the average rate of the train was 20 miles per hour faster than the average rate of her car. We don't know the average rate of each. All we know relatively is that the train traveled on average 20 miles per hour faster than the car. Okay, so any questions on the background information there? There might be some other things you could figure out based on what they've given you. I think there's one thing that relating to a distance that you could figure out. And we're going to need that in a little bit. Okay, so what I want to do is find an algebraic representation that represents the time it takes for her to complete the trip. Okay, and the variable we're going to use is x, and that'll represent the speed of the car. Okay, so in other words, I want to come up with a formula so that if you tell me how fast she was driving in the car, I plug that number in, and it will automatically tell me how long it took her to complete the trip. Okay, taking into account all this information. Okay, so what we'll do is just kind of start with big picture, like an idea, and then we'll kind of worry about translating our idea into symbols and an equation. Okay, so the total time. What's the total time going to equal? Like let's start with how many modes of transportation is she taking to complete her trip? Crazy? 2. So she's going to have 2 times. One for the time she spends what? Yep. In the car. And the other one is going to be the time on the train. And what would we do with the 2 times? We're going to add them. So the total time for the trip is going to be time in car plus time on train. Now we have to figure out how do we represent time in car and time on train using the formula we have and the information we were given. Let's start with the time in the car. If we're doing things with time, we're going to want to use that formula, but we're going to want to solve it for time. So what does time equal? Sam?
Distance over rate.
It's distance over rate. So the time in the car is distance in car divided by rate of car. So let's see if we can figure out the distance. Okay. What's the distance she traveled in the car? 30 miles. And what's the rate of the car? Rebecca?
20 less than the train.
It is 20 less than the train. I agree, but do they give us a way they want us to represent it? So we're going to make everything relative to the speed of the car. So we'll compare the speed of the train to the speed of the car rather than the other way around. So how do they tell us to represent the speed of the car? X. So we'll just, that'll be kind of our basis of comparison for everything. Okay, so there's the time in the car, 30 over X. Time in the train. That's going to be distance in train divided by rate of train. Okay. What's the distance that we travel in the train? This is the one that wasn't given to us, but we've got enough information to infer it. Theo?
40 miles.
Let's go back up and see. So she traveled 120 miles, and she did 30 of it by car. So how much did you say?
40 for train.
So this is the total distance she traveled, right?
Oh, wait, no. 90.
That's okay.
I was doing division for some reason.
So yeah, 120 miles by train minus the 30 gives you 90 on the train, 30 in the car. And now what's the rate of the train? We have to express it like Rebecca did. Similar way to that, relative to the car. Not 20x, that would mean the train is 20 times as fast as the car. If you did 20 times x. But it says the rate of the train is 20 miles per hour faster than the car. So do you know what you would put? Yeah, you put x plus 20. Okay. So there's your time you spend on the train. And now we'll just add the two together. So the total trip time is going to be 30 over x plus 90 over x plus 20. That's how long it'll take her to do her trip. Okay, and we're going to come back to this formula. We're going to use it for a few things. Eventually, we're going to combine it into one fraction with a common denominator. But for now, we can just leave it like that. Any questions on that? You could draw a diagram for this problem, but I don't really think the diagram is overly necessary or helpful. I think if you can figure this out, the big idea of adding two times together, and then use your distance equals rate times time formula. I think that's all you really need. All right, so now we're going to take that formula, and we're going to find out some different things about it. We are not graphing it by hand, okay, but we are going to find the asymptotes, the zeros, the EBM, and a complete graph. First thing I'd like to do is combine it all together into one fraction. I'm not saying that this is wrong, but for certain things, it's not the best way to write it. Okay, for the EBM, it's not the best way to write it. Okay, you need it all combined together. Okay, so my common denominator would just be the product of the two that I have, x plus 20. And what is the first fraction missing to make it have a common denominator? Sam? It's missing x plus 20. So I'm going to multiply top and bottom of this fraction by x plus 20. So that's going to give me 30x plus 600. Now, what is the other fraction missing to have a common denominator? Dylan?
X.
It's missing x. So I'm going to multiply top and bottom by x. Okay. Already did it in the bottom. In the top, I get 90x. Okay, so if we combine all that together and distribute, we get x squared plus 20x in the bottom. And what do I get in the top? about, Shauna, what do I get in the top?
120x plus 600.
Yep, 120x plus 600. All right, so now let's go through and find everything they want to know. Okay, asymptotes. Let's do the vertical asymptotes first. Someone remind me again, how do you always find vertical asymptotes? Rebecca? Get the denominator equal to 0. Can you tell me the two numbers that would make the denominator 0 in this case? No, 10 and 2 wouldn't work. Because if you think about it, if you plug in 10, 10 plus 20 would be 30, and then 30 times 10 would be 300. And help her out. What do we think the two numbers would be that would make that 0? So it's already factored. So now we just have to set each factor equal to 0. Sam, can you just give me one of them?
0.
0. I agree with that. And now do you think you could give me the other one? Rebecca, yeah, you see the other one now? So he set this factor equal to 0, the x. What do you get if you set the other factor equal to 0? Not sure? Yes.
Negative 20.
Okay, negative 20. I'm not saying the negative 20 makes sense as a speed in this problem, but those are the two vertical asymptotes. Any questions on that? Yeah?
Can you re-explain like the denominator, like how you do
So we're looking at that. So you're going to set the first factor equal to 0, and then set the second factor equal to 0.
Oh, okay.
Well, when you set the first one equal to 0, it's already done. The second one, you just subtract 20 from both sides, and there's your other one. Okay, so there's your vertical asymptotes. Let's do horizontal. What do we usually use to help us to find the horizontal asymptotes? We find this first, Jane?
And behavior model.
Yeah, let's find the EBM, which is something else we have to find anyway. Can you tell me what the EBM would be here?
It would be 120x
Over x squared, which becomes 120 over x. There's your end behavior model. What happens to that fraction is x gets really big. Yeah.
It gets really small.
And approaches?
Negative infinity. Or maybe 0.
0. It approaches 0. Yep. Okay, so we've got our vertical asymptotes, horizontal asymptotes, end behavior model, the roots. Okay, so the roots are basically where it crosses the x-axis. It's when this value is equal to 0. So for this one, I think it's a lot better to look at the fraction the way we rewrote it. How can a fraction equal 0? Yeah?
No, I just have a question. So whenever there's an x on the bottom in the EBM, it's always going to approach 0?
As long as there's no x on the top.
Oh.
But there shouldn't be, because if you canceled everything out properly, there should only be x's in the bottom or the top, not both. Yeah. All right, so how would we make a fraction equal to 0? How does that happen?
You take 0?
Right, get the numerator equal to 0, and that will tell you where you cross the x-axis. That'll tell you when y equals 0. All right, so this is the zeros. There might be more than one, there might only be one. I think in this problem there's only one, because the numerator is linear. Okay, so when you solve that, you get x equals -5. Again, I'm not saying that makes sense, because x represents the speed of the car, but algebraically that's what the root is. Okay, so any question on finding the asymptotes, the zeros, or the end behavior model? Right, so the last thing they want is a sketch. Okay. So when you sketch it, you can sketch the way we rewrote it if you're pretty confident you did it right, or just sketch the original. I think I'll just sketch the original.
How do you solve for the y-intercept?
For the y-intercept,
Yeah.
if they asked for that, which they didn't here, you would plug in 0 for x. You would have a problem though if you did that, because if you plug in 0 for x, that's a vertical asymptote, which means this graph will never cross the y-axis. So in this case, that would be impossible to find.
But when you try to find a y-intercept, you just plug in x for, 0 for x.
If you wanted to find it, yep. But again, I didn't ask for that here because it's impossible to find. All right, so let's graph 30 over x, and I'll put it in parentheses, plus 90 divided by, and then I'm going to put parentheses again, just like that. Okay, so for my window, let's see. They said find a complete graph of that equation. They didn't say find a complete graph of the problem situation. So like if somebody walked in right now and just looked at that equation, they would have no idea that it's about a car. That doesn't say anything about a car on this page. So we need to find a complete graph of that equation. Okay. So we know we're looking for vertical asymptotes all the way by -20. So let's set our x min to -40. Let's do +40. And whenever you have vertical asymptotes, it's going to go to infinity and -infinity. So let's just try -10 to 10 and see how it looks. All right, so in terms of our problem, there's really only one section of this graph that makes sense. That's where speed is positive. But if you want to look at the negative section, here's your vertical asymptote at 0. Now, the other vertical asymptote you're not seeing as much because I would have to zoom down more so you could see this continuing and see that going up. But if you did, I think your other vertical asymptote would be right around -20. I'll back it out a little just so you can kind of see it better. Now I think it's a little clearer. -20 and 0. Okay, so there's a complete graph. And if you want the window for that, I used those values. Okay, any question on that? Alright, so now we can use that graph to figure out anything we want. We could say, like, let's say her trip took an hour. How fast was she driving in the car? Well, we'll use that and figure it out. So this one says Sue had 2 hours to complete the trip. How fast was she going in the car? And you could also find how fast she's going in the train, because if you know the car, the train was just 20 faster. Okay, so does our graph represent the speed of the car or the speed of the train? Which one? Dylan?
The car.
Yep, x was the speed of the car, not the train. So if she completes the trip in 2 hours, let's put a line at 2. You know what I'll do? Let me reset that. Put a line at 2. And that's not quite going to do it. Let me do, I don't need to set my x min at -40. Even though it might cross it in the negative speed doesn't make sense. Let's set her speed up to 75. And let's do -10 to 10. I think that'll show the intersection a lot better. Okay, so if she takes exactly 2 hours, well, I guess this problem technically says she has up to 2 hours to complete her trip. second calc intersect. So how fast does she have to go to complete her trip in 2 hours or less? Well, Trevor, how fast does she have to go?
You say the question again, please?
How fast does she have to go to complete her trip in 2 hours or less?
I'm not sure.
Would you say greater than or equal to 46.45?
Yeah, greater than or equal to that speed. Okay, she can't go less than that speed because if she goes slower, then her trip is going to take longer. But if she has 2 hours to complete the trip, graphically, she has to go at least 46.46 miles per hour. Okay, so speed is greater than or equal to 46.46. Okay, now that's graphically. Now they also wanted us to do it algebraically. All right. So to do it algebraically, set her time equal to 2. Okay? And I'm going to do it in the rewritten equation. That's all one denominator. So we've got 2 equals 120x plus 600 divided by, is it x squared plus 20x. Okay, what would be my first step to solve that equation? But, Tessa, what would be my first step? Yeah, what would you multiply each side by? Exactly. If you multiply each side by the denominator, that's going to at least get rid of that fraction. So you'd have 2x squared plus 40x equals 120x plus 600. And now, what kind of equation do we have? Oh, Juliana? What kind of equation is that? Well, look for the highest exponent, and that will tell you. Okay, so if you graph it, it would be a parabola, but what kind of equation is it? Remember the type of equation that gives you a parabola? Ends with a Q?
Oh,
Quadratic. So when you solve a quadratic, what do you get it equal to?
0.
Yeah, so let's get it equal to 0. So 2x squared. I'm going to subtract 120x. And I'm going to subtract the 600. Now we just use quadratic formula. If you want to divide everything by 2, you could do that first. So we've got x squared minus 40x minus 300 equals 0. And does anyone need me to go through the quadratic formula, or can I just tell you the 2 answers you would get? Everyone feels okay with quadratic formula? Okay. So if you go through the whole formula, you would get x equals 20 plus or minus 10 root 7. Now, because we're talking about a speed, which answer doesn't make sense? Yep. Yeah, the negative. If you do 20 minus 10 times the square root of 7, you're going to get a negative number. Let's just check that and see if we get 46.46. 20 plus 10 square roots of 7, and you get 46.46. So you can get exactly the same answer using quadratic formula. What's the advantage of doing it Graphically versus algebraically. It's faster. What's the advantage of doing it algebraically? That graphically can't do. Yeah?
Like if we didn't have the graphing calculator, you wouldn't have been able to graph that accurately on a piece of paper.
Okay, yeah, graphing could be a real pain. You'd never be able to do a graph like that by hand. Yeah, you have to use the calculator. But what's another advantage to doing it algebraically? Yeah?
You get the exact answer.
You get the exact answer. That is the only way to get the exact answer. Okay. Graphically, you can't. All right, so in that example, we got to be careful because we multiplied both sides by something with a variable. Okay, Tessa told us we're going to multiply both sides by x squared plus 20x, which is okay, but what can happen is you might end up with what we call an extraneous solution. What that means is somehow you've done something that created a new answer to the problem that is not an answer to the original problem. So you did an operation that created this new answer that works in your new equation, but it does not work in the original equation before you modified it. And it's not that you did something wrong, it's just that's called an extraneous solution. Okay, so when we have an extraneous solution, we just have to check our answer. Okay, and if you're like, well, how could you do something that creates an extra solution? If you look at this problem, what's the solution to x minus 1 equals 0? What's it?
1.
1. Okay, so that's the answer. Is there any other answer to that problem? No, there's no other answer. But watch what happens if you multiply both sides by x. You would get x squared minus x equals 0. Now you could factor out an x. And now you could set each factor equal to 0. Well, if you set that equal to 0, you get x equals 0 as an answer. And if you set that equal to 0, you get x equals 1 as an answer. Well, where did this 0 come from? 0 is definitely not an answer to the original problem, but it is an answer to the new equation we created. So this 0 will be what you call extraneous. So any questions on the idea of an extraneous root? Okay, it's not always as obvious as that. That's a very, very simple equation. So the way you check for extraneous is you plug it back in. Usually something is extraneous if it causes you to divide by 0 in these types of equations. Okay, so let's try one. And we're going to do the same approach we did last time. We want to get rid of the fractions. So what we do is we multiply everything by the LCD. Now, before I start, I want to factor the denominator on the right-hand side so you notice something. Does anyone see what x squared minus 4x plus 3 factors as? Leo?
X minus 3, x minus 1.
Yes, it factors as the two other denominators you already have. That doesn't have to happen, but most likely in the problems I give you, it will, because it just makes things work out nice. Okay, so the LCD here, the least common denominator, is x minus 1, x minus 3. Megan, what's the first fraction missing to make it have a common denominator? Which one is it missing?
X minus 3.
Yeah, it's missing the x minus 3. So I'll show you what we're going to do. We're really going to multiply everything by x minus 1, x minus 3. But really, the only thing that matters is what she just said, the x minus 3, because the x minus 1s are gone. Okay, let's do it again here. X minus 1, x minus 3. What cancels out there?
X minus 1.
Yep. No, the x minus 1 canceled in the first one. Yeah, the x minus 3. Yep. So the x minus 3 is gone. And let's do it here. What cancels out there? Sam? Well, yeah, the whole thing. That cancels that. So now let's write down what you have left, and remember, anything that you have to multiply is a distributive. So Dylan, what do I get in my first numerator?
2x squared minus 6x.
Perfect. My second one, it's a distributive, but not really anything's happening. It's just x minus 1. And my third fraction, there's nothing to distribute because the denominator canceled. Okay. So now, Juliette, what kind of equation do we have there? We have a quadratic. Yep. And what do we get it equal to? We get it equal to 0. So 2x squared minus 5x minus 3 equals 0. And that one you don't need quadratic formula. It does factors 2x plus 1, x minus 3. Okay. Caleb, if I set the first factor equal to 0, what would I get for x?
X equals -1/2.
Good, -1/2. If I set the second factor equal to 0, Tanya, what do I get? 3. And those are our answers. But make sure you check them. There's 3 possibilities here. They both work. One works, one doesn't. Or they both don't work. Okay? So let's start by checking 3. Could I plug 3 into the original problem? Sam? No, why not?
You divide by 0.
Yeah, I would have a divide by 0. So 3 is extraneous. It's not that we did anything wrong, it just doesn't work. So if you did that on the test and you didn't cross out the 3, I would take a point off because the 3 doesn't work. Now if you check the -1/2, you're fine. -1/2 minus 1, that's not 0. Okay. Basically, as long as you don't get 1 or 3 as your answers, you're good. Okay. Anything else would be fine. Okay. So the only answer to this problem is -1/2. Any question on that one? Okay. Let's try this one. Notice again, if you factor that denominator, this time I put it all on the same side, it's equal to 0. That's fine, because if it's a quadratic, you're going to have to do that anyway. So this is what was on the other side last time. But it's fine to move it to that side. And Jan, how does that factor? That denominator.
X plus 2 and x plus 0.
Yeah, so it's x plus 0 and x plus 2, which is exactly the other 2 denominators we have. So multiply everything through by x plus 2. X plus 2, x plus 2, x plus 2. Abby, what's going to cancel out in the first fraction?
X.
X. Shauna, what's going to cancel out in the second fraction?
X plus 2.
X plus 2. And Gracie, what's going to cancel out in the third fraction? The whole denominator. Okay, multiply what you have left. So we're going to get x squared plus 2x minus 3x minus 6 plus 3x plus 6 equals 0. Okay, combine like terms. We get x squared plus 2x. That's it. The 6's are going to cancel. So now factor that. So it's x times x plus 2 equals 0. And what would make the first factor 0? Dylan?
0.
And how about the second factor?
-2.
-2. Is 0 an okay number to plug into my original problem? No. Is -2 an okay number to plug into my original problem? No. Both of those numbers cause me to divide by 0. That means this equation has no solution. Neither answer works. So this one, it says, at what possible rates could Sue travel to make sure she completes the trip in less than 2.5 hours? Well, to solve it graphically, I still have it typed in. What I would do is just take the equation, put a line at 2.5, and you're going to find the speed that would be right here. Let's just call it A comma B. Now, once you find the speed, you're interested in A. That's the speed. B, we already know, actually I can write B in. B is 2.5. So what speed would she have to travel at to complete the trip in less than 2.5 hours? Her speed would have to be, don't use equal, you're going to use inequality.
More than A.
It would have to be more than A. So her speed is greater than A. Okay, if she wants to complete the trip in less than 2.5 hours, she's got to be going faster than A. If it said she wants to complete the trip in less than or equal to 2.5 hours, then I would have said her speed could have been greater than or equal to A. Right? So you just have to find A using an intersect. But we've done that before. And notice this, because it's an inequality symbol, that makes it something that's not an equation. So that's an inequality. So the last thing we'll finish up with is an example of solving a rational inequality. Okay, remember that if you do graph something, you can have hidden behavior. We've seen things that might look straight, but they're actually curved, or things that are off the screen.
Can inequalities have extraneous solutions?
Can inequalities have extraneous solutions? Well, you only get an extraneous solution if you multiply or divide both sides by a variable. When you solve inequalities, what's the one extra thing you have to be careful about that you don't with an equation? Yeah?
If you multiply or divide by a negative, you flip the sign.
Right. If you multiply or divide by a negative, you would have to flip the sign. So if you're multiplying or dividing both sides by a variable, how would you know if you should be flipping the sign or not? So if the only way you can get an extraneous solution is when you multiply by a variable, we can't do that when we're solving inequalities because of the reason I just said. You wouldn't know if the variable is positive or negative, so you wouldn't know if you should be flipping the sign. So the only way we can solve algebraically is a method we've done before, which is a sign chart. We make a pattern. So this relies on the problem being factorable. If it is not a factorable problem, we are not going to be solving it algebraically. Okay, so I'll do one algebraically. If we want, we could do one graphically, but I don't really think we need to do too much on the graphical stuff. But people can let me know if they want one graphical. Okay, so let's solve that. Now I can't multiply both sides by 2x squared plus 5x minus 3 to get rid of the fraction, because I don't know if that's negative. Could be if you pick the right value for x. So the only way I can do it is to get it 0 on one side, everything else on the other. All right, so let's leave all this where it is. And how would I get 0 on the right side? What would I have to do? Theo?
Subtract 1 from both sides.
I would subtract 1 from both sides, but I'm not going to write it like that. I'm not going to write 1 as minus 1. Okay. I want to write it like this. Can someone tell me why that is the same as minus 1? Yeah?
Because anything over itself is 1.
Yeah. I just wrote 1 a really complicated way, but there's a reason why I did that. Does anybody know why I wrote the number 1 that way? Has to do with something else in the problem. Yep.
So you have common denominator.
Right, I wanted to have common denominators. So now what I can do is just write 2x squared plus 5x minus 3, and I can combine everything that's in the top. 2x squared minus 2x squared. Okay, that minus is distributed. Okay, remember that. What's 2x squared minus 2x squared? Trevor?
0.
0, that's gone. What's 6x minus 5x? Crazy? Yeah, x. So 6x minus 5x, and then negative 8 plus 3. What's negative 8 plus 3? Leo?
Negative 5.
Negative 5. Now I said that this is only going to work if it's factorable, so we're going to hope that what's in the bottom is factorable. And it is. 2x minus 1, x plus 3. So 2x minus 1, x plus 3. And now from here, we do what we've done before. We make a sign chart. What value would you plug into the top to make it 0? Jan? 5. What if you plug numbers smaller than 5 into this expression? What kind of answer would you get?
It's going to be negative.
Would be negative. What if you plug in numbers bigger than 5 into that expression?
It would be positive.
It would be a positive. Okay, let's do the next one. 2x minus 1. What value would you have to plug in for x here to make that 0? Sam? I'm sorry, Caleb?
1/2.
Yeah, 1/2. So you got 1/2. And now, what would you get, Caleb, if you plug in numbers smaller than 1/2?
Negative.
Yep, you get negatives. What if you plug in numbers bigger than 1/2?
Positive.
Positive. Okay, let's do one more. X plus 3. Negative 3 is the root. If you plug in numbers smaller than that, you get negative. Bigger than that, you get positive. So now let's put those all on the same number line. If you want to just jump to the same number line right away and not do them individually, you can. I think that's a little confusing. So we've got negative 3, 1/2, 5. That is not to scale. Okay, I just need my sections, my 4 sections. That's all I need. So let's look at what happens if we plug a number that's negative 3 into all of them. Less than negative 3. Okay. If I plug a number less than negative 3 into the top one, what do I get? I get a negative in the top divided by, let's check the next one. What if I do less than negative 3 in the first one in the bottom? A negative. And what if I do less than negative 3 for the second one in the bottom? A negative. What's a negative times a negative? positive. And what's a negative over a positive? Negative. Let's check between -3.5, but the idea is it alternates negative, positive, negative, positive. But let's just check one more. Between -3.5 in the first one, let's see. Yeah, what would I get there? Negative. Between -3.5 in the second one, that's negative. And between -3.5 in the third one, positive. What's a negative times a positive? A negative. And a negative over a negative? Positive. So it's just going to alternate. And now the question was, where is this negative? Where is it less than 0? How many sections on that number line are negative? 2. In that section, we will be less than 0. And in that section. Can anyone describe to me the interval that I circled right there? Yep.
From -infinity to -3.
Yep.
And then from a half to 9.
And again, I used parentheses because it didn't say equal to. Also, you would want to use parentheses because if you didn't, you wouldn't want to include the number 3 in anything. Because if you did, that's a divide by 0. I'm sorry, -3. Okay, so you always use parentheses because those numbers cause you to divide by 0. Okay. So no, you don't really have to worry about extraneous roots here because we have a totally different method to solve it.
So when you're solving an inequality, you want to get the intervals?
When you're solving an inequality, you always want to get the intervals. Yep. And then if you couldn't solve it algebraically, you could just graph it on your calculator. I would graph this in y1, put that in y2, and look at where they cross. Okay? Look at where the graph in y1 is above the graph in y2. So you're going to have to calculate some intersects. Okay? Keep in mind it might do something like this. So if it looked like that, I would say it's above in this interval, that interval, and that interval. Okay, so you just have to find some intersection points. Okay, I don't know if it's going to look exactly like that. All right, so homework tonight, okay, it's 1 through 9 and 11 through 17. So I guess I could just say 1 through 17 odd. That might be simpler. So 1 through 17, odd. 20 to 22. 24, 28, 31, 32. Okay, so we have our last test of the term tomorrow. I'll be after school today for extra help. And make sure if you owe me anything, we just have to get it wrapped up by tomorrow.